Hello everyone. In this video, we shall continue discussing Hess's law. Specifically, I will be teaching method 3 for determining enthalpy changes of reactions using Hess's law, which is manipulating equations. As you know, as we've learned so far, we've learned method 1, which is constructing energy cycles to determine the enthalpy change of a reaction using experimentally determined values for the enthalpy changes of combustion or formation. We also use the general equation, the general mathematical equation, which I call method 2, which is this one over here. For example, when given delta H combustion values, the general mathematical equation you could use is the delta H of reaction is determined as the sum of the enthalpy change of combustion of reactants minus the sum of the enthalpy change of combustion of products. This is called method 2. I will go over method 1 and method 2 briefly and apply method 3 to the same examples we did last class. I've written an example here which was covered in the previous videos. 1 mole of C2H2 reacts with 2 moles of H2 to produce 1 mole of C2H6 gas. we were asked to determine the delta H of this reaction when given enthalpy changes of combustion values for both reactants and products, which are listed here. What we did, since we're given enthalpy changes of combustion values in kilojoule per mole, thus this is an enthalpy change. This is a enthalpy change of combustion cycle, and we would place CO2 and H2O at the bottom here, according to the definition, since the definition states that the enthalpy change of combustion is the enthalpy change when 1 mole of a substance undergoes complete combustion under standard conditions, which forms CO2 and H2O. Thus, the arrows will all be pointing downwards, as discussed previously, towards CO2 and H2O. In this reaction, we have 1 mole of C2H2, 2 moles of hydrogen gas, and 1 mole of C2H6 products produced. Thus, the enthalpy change of combustion per mole of C2H2 is negative 1,300, and I have 1 mole here. Thus, we place negative 1,300 on this arrow here. I have 2 moles of hydrogen gas being combusted. Thus, I would multiply the molar value for the combustion of hydrogen by 2, as placed on this arrow here. And I have the molar enthalpy change of combustion of C2H6, which is negative 1,560, which I placed on this arrow here. And to calculate the enthalpy change of reaction, we go through this new pathway to determine this enthalpy change of reaction. So we go from reactants towards the CO2 and H2O box, and then towards the products as discussed in my previous videos. So this normally translates into the sum of the enthalpy change of combustion of reactants subtracted from the sum of the enthalpy change of combustion of products. Thus, this would be listed as negative 1,300 plus 2 multiplied by negative 286, subtracted from negative 1,560, because the arrow in this direction is exothermic. Thus, we're going to move against the arrow or opposite in the opposite direction, which would render this reaction endothermic. Thus, this is why this negative sign was placed here. It's to convert the negative 1,560 into a positive. The third method, which is manipulating equations, you would normally be given these enthalpy change of combustion values according to the definition or as equations, as I listed here. Thus, I rewrote the equation we need to determine the enthalpy change of reaction for, and you would be given these 3 equations. If you look closely, this is the enthalpy change of combustion per mole of C2H2. This is the definition. It's when 1 mole of C2H2 undergoes complete combustion to form CO2 and H2O. This is the definition for the enthalpy change of combustion of 1 mole of H2 gas to form H2O. There's no CO2 gas formed here since it's only H2. There's no carbon atoms in the reactants. And this is the enthalpy change of combustion per mole of C2H6 to form CO2 and H2O, and these equations have been balanced. Normally in an exam you would be given all these equations. Thus, I'm given the value for the combustion per mole of C2H2, I'm given the value for the combustion per mole of hydrogen gas and the combustion per mole of C2H6 gas. We need to manipulate these equations to form this equation over here. This is what's written on top here. In method 3, we rearrange the equations for the data given. This is the data given, these 3 equations here. to produce the equation for the reaction corresponding to the enthalpy change we have to find, which is this reaction over here. The way to do this is you start by finding your reactants and products in the equations listed below. Thus, C2H2 here, I have 1 mole of C2H2 in the main equation, and it's a reactant. And it's over here in the first equation, it's a reactant, which is the same. Thus, we're good to go in terms of its position as a reactant or a product, and I have 1 mole. Thus, this equation is ready. No need to manipulate this equation. On the other hand, H2 gas is a reactant, and I have 2 moles of it. In this equation, H2 gas is a reactant, but I have 1 mole. Thus, what should be done here is this whole equation will be multiplied by 2. This equation will be multiplied by 2 times this whole equation, and this value will also be multiplied by 2 since this is per mole, and I just multiplied it by 2 to produce 2 moles as in the equation. As for the C2H6 product, the C2H6 product, it's a product, while here it's a reactant. I have 1 mole of C2H6 here, and I have 1 mole of C2H6, so the molar quantities are fine, but its position is incorrect. It needs to be a product, not a reactant. Thus, I would flip this equation. I would write it the other way around. Thus, instead of being exothermic in this direction, I would write it in the opposite direction as an endothermic reaction, and we would flip this sign. So this needs to be flipped. So this needs to be multiplied by 2. This is fine. The first equation is okay. The second equation needs to be multiplied by 2. The third equation needs to be flipped, which I manipulated on the bottom here. Thus, as I stated, the first equation was kept the same right there. This equation was multiplied by 2. All the factors were multiplied by 2, the stoichiometric ratios. So this was 1 half 1. It became 2 1 2. And this equation was only flipped. As you can see, it's written in the opposite direction now to place the C2H6 as the product, and its sign was flipped. Thus, when you multiply an equation, you multiply the whole equation along with its number. If you had to divide an equation by 2, you divide the whole stoichiometric ratios by 2, and you divide the enthalpy change of its reaction by 2. If you had to flip the equation, then you would have to flip its sign. Manipulating these equations, this is now ready. This would be our answer, but to check if your manipulation was correct, you would have to add these equations together. Thus, any substances that appear on both sides of an equation, in different equations, will be subtracted from one another, while if they are on the same side of the equations as in oxygen here, they will be added. Thus, for example, I have 2 moles of CO2 on this side, and I have 2 moles of CO2 in the products here. Thus, these two would cancel each other out, because any substances on opposite sides you subtract. If they're on the same sides, they are added. Thus, 2 CO2 would cancel out with 2 CO2. I have 1 H2O and another here, and another 2 here, which total up to 3 molecules of H2 in the products, and I have 3 molecules of H2O in the reactants. Thus, these 3 would cancel with these 3. I have 2.5 moles of oxygen gas as a reactant and 1 mole of oxygen gas as a reactant, which brings the total to 3.5 oxygens as reactants. And thus here I have 3.5 oxygen. This would cancel out with these 2. Thus, if I were to add all 3 now, just as you would in simultaneous equations in math, this equation, you just bring down what's left in the equations. Thus, this adds up to C2H2 gas plus 2H2 gas would produce C2H6 gas, which is the same as the equation asked for in the reactions. Thus, since this equation now matches the equation in the question, you simply add these values. Thus, the delta H of this reaction would equal to negative 1,300 plus 2 times negative 286 plus 1,560, which is the exact same answer as that derived using methods 1 and 2 over here, which was negative 1,300 plus 2 times negative 286 plus, since these two negatives multiplied would form a positive sign, thus plus 1560. And this is how you manipulate equations to calculate the enthalpy change of a reaction. I used this example in which we were given enthalpy change of combustion equations. I'm going to do another example to manipulate the equations using method 3, and I'll go over what we learned last class, the first two methods, if we're given enthalpy change of formation values, as in this example here. Thus, this example, you have 1 mole of C3H8 reacting with 5 moles of oxygen gas to produce 3 moles of CO2 gas plus 4 moles of H2O liquid, and we're asked to calculate the enthalpy change of this reaction when given enthalpy change of formation values over here. The enthalpy change per mole of C3H8 is negative 105. The enthalpy change per mole of CO2 is negative 394. The enthalpy change of formation of H2O per mole is negative 286. Thus, since we're given enthalpy change of formation values, using method 1 to construct the cycle, the first thing we would place here are the elements that make up either the reactants or products, and they should be balanced as we covered in our previous videos. And the arrows would be pointing upwards towards the substance according to the definition of enthalpy change of formation, which is the enthalpy change when 1 mole of a substance, such as C3H8, is formed from its elements. Thus, all the arrows for a formation cycle would be pointing upwards, as stated previously. The value for the formation of 1 mole of C3H8 is negative 105. The value for the formation of 3 moles of CO2 is 3 multiplied by negative 394, and the value for the formation of 4 moles of H2O is 4 multiplied by negative 286, and thus you have a complete cycle. The last step would be to move from reactants towards the products through this new pathway, and we do not have an enthalpy change of formation for oxygen since it's already in its elemental form or standard state. Thus, its enthalpy change of formation is 0. Thus, moving from reactants to products through the cycle, this arrow here would need to be flipped. And thus, if it's an exothermic in this direction, the opposite direction would be endothermic, and thus this would be converted into a positive sign. And these two would remain the same, and then they would be added. Or using method 2, which is the mathematical equation, general mathematical equation when given enthalpy change of formation values, this would be the sum of the enthalpy change of formation of products subtracted from the sum of the enthalpy change of formation of reactants, which is the same as adding these two arrows here and subtracting them from this arrow here, which produces 3 moles of 3 multiplied by negative 394, which is this arrow here, the products, plus 4 multiplied by negative 286 with no changes, subtracted from negative 105, which would convert this to a positive 105. This same question can be given in terms of manipulating equations, which I will cover down here to produce the exact same answer. Thus, in this equation, which is the same exact equation above, we're given the enthalpy changes of formation equations according to the definition per mole of C3H8, per mole of CO2, per mole of H2O from their elements, and their values are listed here. We need to manipulate these equations to form this equation above. Thus, as stated previously in the previous example, I would start with the C3H8, which is a reactant here, and I would look for it in the equations here, and it's a product here. Thus, this equation needs to be flipped, written in the opposite direction, and it's 1 mole here, and it's 1 mole here, so we're good to go with moles. So this equation would need to be flipped. Thus, I would flip or reverse this equation. On the other hand, this equation, the CO2 is a product, and the CO2 here is a product. We don't look at the oxygens. These would because we don't have a value for the enthalpy change of formation of oxygen, just don't consider the oxygens when manipulating equations. This carbon dioxide is a product here, it's a product here, but we have 3 moles of CO2 here, thus this would need to be multiplied by 3. Thus I would multiply this whole equation by 3 and the value by 3. As well as the H2O, it's a product here and it's a product in this equation, so its position is fine, but it needs to be multiplied by 4 moles since I have 4 moles of H2O in the equation. Thus this equation will be multiplied by 4. I have manipulated these equations below, as you can see here. Equation 1 was flipped. As you can see, it was written in the opposite direction here, and its sign was reversed into a positive sign, since if this reaction is exothermic in this direction, then the opposite direction would be endothermic, and this is why its sign is flipped. As for this equation here, we said we need to multiply it by 3, and the whole stoichiometric ratios will multiplied by 3 as well as its value. And the same was done for H2O. It was multiplied by 4, and the whole stoichiometric ratios were multiplied by 4, and its value was multiplied by 4. Thus, to make sure that these would add up to the equation given given in the question that we are required to find the enthalpy change of a reaction for. Once again, any substances that are on opposite sides of the equations would cancel out. Thus, I have 3 carbon atoms here would cancel out with 3 carbon atoms here. I have O2, I have 5 O2 here, nothing to cancel it on this side. I have 4 H2 molecules here, which would cancel out with 4 hydrogen molecules here. And nothing else would cancel or add up, except these two would add up because they're on the same side. Thus, if I were to write the overall equation, it would come up to C3H8 gas plus 5O2 gas, which produces 3CO2 gas plus 4H2O liquid, which is the same as that given in the question. Thus, since this overall equation is correct, I would simply add these values here. So the delta H of this reaction would come up to positive 105 plus 3 multiplied by negative 394 plus 4 multiplied by negative 286, which is the exact same answer we got using method 1 or 2, in which the negative 394 was multiplied by 3, the negative 286 was multiplied by 4, and the sign of the first equation was flipped into a positive sign. I would like to do one more example to cover this method, which I listed here. As you can see, whenever you're given a question in which the equations for the enthalpy changes of the reaction data that's given are listed, you would use method 3 to solve this question, since it's the easiest method. In this case, we have 1 mole of CO2 reacting with 1 mole of H2 to produce 1 mole of CO plus 1 mole of H2O. That's this equation. They're all 1 to 1 to 1 to 1 stoichiometric ratios. Thus, we won't have to worry about moles in the equation. Let's consider these equations here. Thus, I would first thing I would look at is the reactants. CO2 is a reactant here, while CO2 is a product here. I have 1 mole here and 1 mole here, so the moles are fine, but its position is incorrect. Thus, I would need to flip this equation to make the CO2 a reactant and the CO as a product, as you can see here. CO2 is a reactant while CO is a product. This equation needs to be flipped, and this sign will be flipped. On the other hand, I'm given the enthalpy change here per 2 moles of hydrogen plus O2 produces 2 moles of H2O. All I need is 1 mole of hydrogen. Thus, this equation would need to be divided by 2. Thus, I would divide this equation by 2 to produce 1 mole of H2, since H2 is a reactant here and it's a reactant here, no need to flip this equation. And the H2O is a product and it's a product here, but once again the H2O is 1 mole in the main equation. Thus, this needs to be divided by 2. And when you divide the equation by 2, this value will be divided by 2 as well. And this is what I did below. The first equation was flipped, written the other way around, and its sign was changed from a negative exothermic reaction to a positive endothermic reaction, while the second equation was divided by 2, and thus the moles were converted into 1, half, and 1, as seen here, and this value was divided by 2. Thus, to check if this forms the overall equation, I would need to add both equations together. and cancel those that appear on the opposite sides and add the same substances that appear on the same side. Thus, I have half O2 here, which will cancel out with half O2 as a product in the top equation, and there are no other common substances. Thus, this equation would translate to CO2 gas plus H2 gas would produce H2O liquid plus CO gas as the question asks. Therefore, to calculate the enthalpy change of this reaction, I would simply add these values. So it's positive 283 plus negative 286, which translates to negative 286. This is method 3 of manipulating equations using Hess's law to calculate the enthalpy changes of reactions. Please solve the attached worksheets, which using method 3 only for manipulating equations, and by midnight tonight. I require it solved by midnight tonight. Thank you for watching.